Imagine an object hurtling through the cosmic void for perhaps millions of years, finally approaching our sun at speeds that would make our fastest spacecraft look motionless. According to every law of physics, we understand when this visitor, 3I Atlas, rounded the sun's inferno on October 29, 2024. It should have erupted in a spectacular display of vaporized ice and dust. It should have blazed with a tail millions of kilometers long, a cosmic banner announcing its passage through our solar system. Instead, it emerged from Perihelion with something that should be impossible: nothing. No tail, no massive cloud of debris, just silence where physics demands a scream. What you're about to discover tonight could fundamentally alter how we understand our place in the universe. This isn't about a disappointing comet that failed to put on a show. This is about an object that accelerated in ways that violate our understanding of natural physics, yet left no evidence of how it did so.
The implications stretch from the purely scientific to the profoundly philosophical, touching on questions humanity has asked since we first looked up at the stars and wondered, are we alone? NASA's Jet Propulsion Laboratory confirmed it with cold mathematical precision. 3I Atlas accelerated with a statistical significance of 3.7 standard deviations. That's not measurement error, that's real. According to the fundamental laws of momentum conservation, this acceleration should have required the object to lose more than 13% of its total mass, over 5 billion tons of material violently expelled into space. Astrophysicist Avi Loeb calculated it using equations that have never failed us before. Yet when the Unravels Observatory in Spain and the Virtual Telescope Project captured images on November 5th, just days after Perihelion, they saw an object essentially unchanged from July. The math says one thing, the images say another. Both cannot be true. How does something accelerate more, yet outgas less? How does an object lose billions of tons of mass without leaving a trace? And perhaps most unsettling of all, what if the answer to these questions isn't found in our textbooks of natural science, but in the uncomfortable realm of technology we didn't create? Tonight we journey into one of the most profound mysteries in modern astronomy. We'll explore the hard science, the inexplicable observations, and the hypothesis that makes many scientists deeply uncomfortable. This is the story of 3I Atlas, the object that physics cannot explain, and the questions it forces us to ask about ourselves, our universe, and whether we've been visited by something far stranger than a simple comet. Long before 3I Atlas entered our solar system, before it became the center of the most intense astronomical debate in decades, humanity was already searching the skies for visitors from beyond. Not out of paranoia, but out of necessity. We call them interstellar objects, wanderers between the stars, nomads of the cosmic void. For most of human history, we didn't even know such things existed. We believed quite reasonably that every object in our night sky was born here in our solar system, gravitationally bound to our sun for eternity. Comets returned on predictable schedules. Asteroids orbited in stable belts. Everything had a place, a history we could trace back to the primordial cloud from which our planets formed. Then came October 19th, 2017. A telescope in Hawaii, part of the Pan-STARRS survey, detected something moving through the inner solar system at an angle and speed that made no sense for a native object. Its trajectory was hyperbolic, the mathematical signature of something that came from the depths of space and was passing through, never to return. They named it Oumuamua, a Hawaiian word meaning scout or messenger. It was the first confirmed interstellar object ever detected passing through our solar system, and it was deeply, fundamentally strange. Oumuamua was elongated, shaped like a cigar or perhaps a pancake, tumbling end over end as it sailed past the sun. But the feature that sparked the most intense debate was its acceleration. As Oumuamua moved away from the sun, it deviated from its predicted trajectory. Something was pushing it. The natural explanation would be cometary outgassing ice, turning to vapor, creating a rocket effect. But Oumuamua showed no tail, no coma of gas and dust, nothing that would indicate it was a comet at all. Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard University, proposed what seemed like an outlandish hypothesis. What if Oumuamua was artificial? What if it was a light sail, a thin sheet of reflective material pushed by the pressure of sunlight itself? Technology, not nature. The backlash was immediate and fierce. The astronomical community preferred any exotic natural explanation. Nitrogen icebergs, hydrogen icebergs, fractal dust, aggregates over entertaining the possibility of extraterrestrial technology. And to be fair, extraordinary claims require extraordinary evidence. A single anomalous object, no matter how strange, is not enough to overturn our understanding of the cosmos. But then came August 10th, 2024. The Atlas survey in Chile detected another interstellar visitor. They designated it C2024S1, but it would come to be known simply as 3I Atlas, the third interstellar object ever confirmed. Initial observations suggested it was different from Oumuamua in almost every way. Where Oumuamua was small, perhaps 100 meters across 3I Atlas appeared massive with a nucleus estimated at 5 kilometers in diameter. That made it roughly 1,000,000 times more massive. Where Oumuamua was tumbling chaotically, 3I Atlas seemed more stable.
And crucially, 3I Atlas showed clear signs of a coma, a halo of gas and dust, marking it as what astronomers call an active comet. The astronomical community breathed a collective sigh of relief. Here, finally, was a normal interstellar object, a cosmic iceberg from another star system behaving exactly as icy bodies should behave. It would pass through our solar system, put on a spectacular show as it rounded the sun, and give us invaluable data about the composition of planetary systems beyond our own. The story should have ended there, but the universe is under no obligation to meet our expectations. Between July and September 2024, 3I Atlas was observed extensively. A staggering 4,022 individual data points were collected from 227 different observatories around the world. And during that entire period, the object showed absolutely no detectable non-gravitational acceleration. Zero. Its motion was entirely consistent with gravity alone. The gravitational pull of the sun, the planets, the subtle influences of Jupiter's immense mass, all perfectly accounted for. 3I Atlas was coasting an inert boulder of ice and rock, following the strict choreography of celestial mechanics. The trajectory was calculated, the perihelion date was predicted, and astronomers prepared their instruments for what they expected to be the astronomical event of the year. Perihelion was scheduled for October 29th. At that point, 3I Atlas would pass within 0.48 astronomical units of the Sun's surface, about half the distance between the Sun and Earth. For a comet, this is an extraordinary test. The solar flux at that distance is intense, capable of heating surfaces to temperatures where rock itself begins to soften. For an icy body, the effect would be catastrophic.
Water ice, frozen carbon dioxide, methane, ammonia, all the volatile compounds we expect to find in comets, would not merely melt. They would sublimate, transitioning directly from solid to gas in a violent, explosive release of energy. This was the show astronomers anticipated from 3I Atlas. With a nucleus 5 kilometers across and a composition presumably rich in volatiles, the spectacle should have been extraordinary. Predictions were made, observation schedules were arranged, and the world waited. The ancient Babylonians called comets hairy stars and viewed them as omens. The Chinese kept meticulous records of comets for over 2,000 years, noting their appearance's brightness and the shapes of their tails with remarkable precision. They believed comets were celestial brooms, sweeping away the old to make way for the new. Perhaps they were more right than they knew. Perhaps 3i Atlas is indeed sweeping away something our certainty that we understand the visitors from the stars. As 3i Atlas descended into the inner solar system through the late summer and early autumn of 2024, it became the most intensely observed interstellar object in history. The lessons learned from Oumuamua's brief passage had fundamentally changed how the astronomical community approaches such visitors. Oumuamua had caught us unprepared. It was discovered when it was already past the sun racing away from our system. By the time we realized what we were seeing, the object was already beyond the orbit of Mars. We had mere weeks to study it before it became too faint to observe. The data we collected was fragmentary, limited, and frustratingly incomplete. This time would be different. The Atlas survey that discovered 3i Atlas consists of 4 telescopes in Hawaii and South Africa that scan the entire visible sky every night. When Atlas flagged the object, the response was immediate and coordinated. Within hours, observatories across the globe were turning their attention to this newcomer. The mathematics of orbital mechanics are unforgiving and precise. Every object in our solar system follows an ellipse, or in special cases a circle or parabola. But an object from interstellar space follows a hyperbola. An open curve that enters our solar system swings around the sun and escapes back into the void, never to return. 3i Atlas's trajectory was distinctly hyperbolic. Its orbital eccentricity was calculated at approximately 3.0. Anything above 1.0 is escaping. Moreover, its velocity relative to the local standard of rest was unusually high, around 80 kilometers per second. This suggested it had been wandering the galaxy for a very long time, perhaps hundreds of millions of years. But trajectory alone wasn't the only unusual feature detected early on. In July and August, when 3i Atlas was still far from the sun, multiple observers reported seeing something that should not have been there, an anti-tail. In comet terminology, an anti-tail is a structure that appears to point toward the sun rather than away from it. This seems to violate the basic physics of comets. Solar pressure should push material away from the sun, not toward it. Anti-tails are not entirely unknown. They can occur when Earth passes through the plane of a comet's orbit, creating a perspective effect. But 3i Atlas's anti-tail was observed consistently over weeks from multiple viewing angles. It was not an illusion. The Very Large Telescope in Chile turned its considerable attention to this feature. Using spectroscopy, the technique of splitting light into its component wavelengths to identify chemical composition, they discovered something extraordinary. The gas surrounding 3i Atlas contained nickel. On its own, this is not shocking. Comets do contain metals, but the ratio of metals was wrong. Profoundly wrong. In nature, nickel and iron are inseparable companions. They form together in the cores of massive stars. They are scattered together when those stars explode as supernovae. Everywhere we look in the cosmos, the ratio of iron to nickel is remarkably consistent, about 20:1. In 3i Atlas, the iron was missing. The nickel to iron ratio was orders of magnitude higher than in any known natural object. The research team analyzing this data made a provocative suggestion. They proposed that the nickel might be in the form of nickel tetracarbonyl, a compound consisting of one nickel atom bonded to 4 carbon monoxide molecules. Here's why this is remarkable. Nickel tetracarbonyl is an industrial compound. On Earth, it is produced through a specific chemical process called the Mond process, used to create high-purity nickel for industrial applications. It is not known to form naturally in the cold, low-pressure environment of comets. The researchers were careful to note that perhaps under exotic conditions, we do not yet understand this compound could form naturally in some corner of an alien star system. But the implication hung in the air like a question that couldn't quite be spoken. What if the chemistry of 3i Atlas reflects not natural processes, but material science? This chemistry became even more puzzling when compared to the previous interstellar comet 2I Borisov. That object discovered in 2019 had chemistry that was boringly normal. Its nickel-to-iron ratio matched expectations perfectly. In every chemical test, 2I Borisov looked like it could have been born in our own system. 3I Atlas, by contrast, was an outlier in almost every measurement. Its nickel-to-cyanide ratio was similarly anomalous, far more nickel relative to cyanide than in any known comet. Statistically, the probability of this chemistry occurring naturally was calculated to be less than 1%. As summer turned to autumn, a geophysicist named Stefan Burns began making an unusual series of predictions. Burns proposed that 3I Atlas's approach would trigger solar activity. His reasoning was based on the idea that a massive object passing through the sun's magnetic field would represent a significant perturbation to the delicate electromagnetic balance. On October 21st, exactly as Burns had predicted, the sun launched a massive coronal mass ejection, a CME, directly toward the location where 3I Atlas would be during its perihelion passage. A CME is not a gentle phenomenon. It is a billion-ton wave of superheated plasma ejected from the sun at speeds that can reach several million kilometers per hour. When a CME hits a comet, the results are typically spectacular and violent. The additional energy can trigger dramatic brightening tail enhancement and, in extreme cases, complete fragmentation. Comet Ison, which approached the Sun in 2013, disintegrated partially due to the combined stresses of solar heating and CME impacts. It approached perihelion as a bright comet and emerged as a dissipating cloud of debris. Meanwhile, observations continued to pour in from around the world. The European Space Agency's Mars Express Orbiter, along with the ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter, were all positioned to observe 3I Atlas when it passed just 30 million kilometers from Mars in early October. But the most valuable images, those from the high-rise camera aboard the Mars Reconnaissance Orbiter, which could have resolved details on 3I Atlas's surface at unprecedented resolution, were not released. These images exist. They were taken on October 2nd and 3rd. But for reasons that remain unclear, they have been withheld from public release. As October progressed, the data continued to accumulate. The ALMA radio telescope array detected 3I Atlas 4 arcseconds away from where it should have been based on gravitational calculations alone. In the precision world of astronomical measurements, this was proof that something was pushing this object off its predicted path. Non-gravitational acceleration had been detected. The same inexplicable behavior that made Oumuamua so controversial was now confirmed in 3I Atlas. The ancient Greeks believed that comets were atmospheric phenomena burning gases in Earth's upper air. It took until the Renaissance for astronomers like Tycho Brahe to prove through careful measurements that comets were actually celestial objects far beyond the moon's orbit. Now in the 21st century, we face a similar revolution in understanding. We thought we knew what comets were. 3I Atlas is teaching us that our certainty was premature. The object was approaching perihelion. October 29th was just days away. And what telescopes were about to witness would challenge everything we thought we understood. October 29th, 2024, perihelion, for 3I Atlas. This was the moment of maximum stress, maximum heat, maximum transformation. The object had been falling toward the sun for months, accelerating under gravity's relentless pull. Now at a distance of just 0.48 astronomical units, roughly 72 million kilometers, it faced the full fury of our star. The solar flux at 3I Atlas's perihelion distance is approximately 4 times what Earth receives, intense enough to boil water, almost instantaneously hot enough to make rock begin to soften and glow. For an icy comet, perihelion is simultaneously a moment of glory and destruction. The intense heating causes volatiles to sublimate at prodigious rates. The nucleus can lose tons of material every second. The expanding gas carries dust particles, creating a massive cloud that can grow to be larger than Jupiter.
Material streams away in two distinct tails, a curved dust tail and a straight ion tail pointing away from the sun. Historical records are filled with accounts of great comets that lit up the sky at Perihelion. The Great Comet of 1680 became so bright it could be seen during the day. Comet McNaught in 2007 developed a tail that stretched across a significant fraction of the visible sky. 3I Atlas, with its 5-kilometer nucleus and composition presumably rich in volatiles, should have put on a show exceeding almost anything in recent history. The predictions were confident. The anticipated brightness increase was calculated, and then the object rounded the sun. The first data came not from optical telescopes, but from spacecraft monitoring the sun itself. The Solar and Heliospheric Observatory captured images of 3I Atlas as it passed through perihelion. These images showed a compact, bright object, but nothing that suggested unusual activity or fragmentation.
More telling were the images from the Punch satellite constellation spacecraft specifically designed to image the region immediately around the sun. Punch observed 3I Atlas at perihelion from multiple angles. The images showed very little. A compact source, no massive expanding coma, no spectacular tail formation. This was the first hint that something was profoundly wrong. Remember, at this same moment, the massive coronal mass ejection that Stefan Burns had predicted was slamming into 3I Atlas. The impact of 1 billion tons of superheated plasma traveling at millions of kilometers per hour. The electromagnetic fields in a CME are intense enough to create spectacular auroras when they interact with Earth's magnetic field. 3I Atlas had no magnetic field protection. It was naked in the solar wind. The CME impact should have been visible as a sudden brightening, a flare of activity, as the additional energy excited atoms in the coma and triggered enhanced sublimation. 3I Atlas brightened, yes, but only by a factor of about 5, entirely consistent with the expected increase from solar heating alone. There was no spike, no sudden jump corresponding to the CME impact. The object passed through the plasma wave as if it weren't there, or more accurately, as if the object had nothing to react with, as if there was no substantial gaseous coma to excite, no surface volatiles to sublimate under the additional energy input. The sun monitoring satellites recorded 3I Atlas's passage and survival. The object emerged from perihelion intact, not fragmented. For a loosely bound rubble pile of ice and dust, which is what most comets are believed to be, this was already unusual. The tidal forces at perihelion can literally tear weak comets apart. Comet Shoemaker-Levy 9 was torn into more than 20 fragments during a close approach to Jupiter in 1992. Those fragments then crashed into Jupiter in 1994 in spectacular impacts that left Earth-sized scars in the planet's atmosphere. For 3I Atlas to emerge intact suggested either that the object was more solid than typical comets, or that it was exceptionally small. But the observed brightness implied it was not small at all. As October turned to November, the astronomical community waited for the post-perihelion observations. This would be the critical test. If 3I Atlas was a normal comet, it should now be surrounded by an enormous cloud of recently ejected material. The tail should be obvious, spectacular, unmistakable. On November 5th, the moment of truth arrived. The Arnavs Observatory in Spain captured new high-resolution images. The Virtual Telescope project in Italy did the same. These were professional-grade images from sophisticated instruments. What they saw defied explanation. 3I Atlas appeared as a compact, fuzzy ball of light. It had a coma, that familiar halo of gas and dust, but the coma was not significantly different from what had been observed in July before perihelion. The overall shape and structure of the object were essentially unchanged. There was no clear cometary tail, none. An object that just passed through the solar furnace, an object that, according to physics, must have lost over 13% of its mass, more than 5 billion tons of material, emerged, looking essentially the same as it did 4 months earlier when it was much farther from the sun and much less active. To put this in perspective, the observers released a comparison image. On November 3rd, Unravels had photographed Comet Lemon, a regular comet from our own solar system. Lemon displayed a clear, textbook-perfect cometary tail pointing away from the sun. This is normal. This is what comets do. But 3I Atlas, which according to the acceleration data should have been outgassing far more violently than Lemon, showed less activity, not more. The physics and the observations were in direct contradiction. NASA's Jet Propulsion Laboratory measured a non-gravitational acceleration with a statistical significance of 3.7 sigma, a real signal, not noise. When Avi Loeb applied the principles of momentum conservation, the math gave an inescapable result. To produce this acceleration through natural cometary outgassing, 3I Atlas would need to eject at least 13% of its mass. For a 5-kilometer object with an estimated mass of 40 billion tons, that means 5.12 billion tons of material was ejected. That much material does not vanish invisibly. It forms a cloud. That cloud gets pushed by radiation pressure and solar wind into a tail. That tail should be enormous, bright, and unmistakable. The tail is not there. Both statements cannot be true.
Either the acceleration did not happen, or it was not caused by natural outgassing. NASA's data confirms the acceleration is real. Therefore, the natural outgassing explanation must be wrong. In the weeks following Perihelion, additional observations came in from other facilities. The Hubble Space Telescope captured images. Ground-based observatories contributed their data. Every observation told the same story, an object that appeared far too quiescent for something that had just undergone massive outgassing. The James Webb Space Telescope, with its unprecedented infrared capabilities, was scheduled to observe in December when it made its closest approach to Earth. Webb's spectroscopic instruments could measure the exact composition and density of any gas cloud with exquisite precision. That observation on December 19th would be the final test. Webb would either detect the 5 billion tons of ejected material, or it would find that the gas cloud was not there.
Each individual observation had possible, if increasingly contrived, natural explanations. But the cumulative weight of the evidence was beginning to exceed what natural explanations could bear. The ancient Chinese astronomers developed a sophisticated taxonomy of comets based on their appearance. They classified comets by the number of tails, their colors, and their trajectories. They believed that different types of comets portended different events. In all their meticulous records spanning thousands of years, there is no description of a comet that accelerated without a tail. Such an object would have been considered impossible, a violation of the natural order. Perhaps they were right. Perhaps 3I Atlas is not part of the natural order. The passage through the solar furnace should have been transformative. Instead, it was revelatory. It revealed that 3I Atlas is something we do not understand, something that does not fit into our categories. The data from December would either resolve this mystery or deepen it beyond anything in the history of astronomy. But as scientists waited, many were beginning to suspect they already knew what Webb would find. Nothing. Or at least nothing like the massive gas cloud that physics demanded. There is a certain beauty in physics, not the aesthetic beauty of a sunset or a symphony, but the deeper beauty of constraint, of law, of knowing that the universe plays by rules that cannot be broken. Momentum conservation is one of those unbreakable rules. It states with elegant simplicity that in a closed system, the total momentum before an event must equal the total momentum after. If something accelerates in one direction, something else must move in the opposite direction. This is not a suggestion. This is as fundamental to the operation of the universe as the existence of time itself. Every rocket ever built operates on this principle. Every comet that has ever blazed across our skies obeys it without exception. When a comet approaches the sun and its surface ices begin to sublimate, the gas molecules that escape carry momentum away. The comet itself recoils in the opposite direction like a rocket. This is called non-gravitational acceleration, and we have observed it in countless solar system comets over centuries. For 3I Atlas, we can measure 2 of the 3 relevant factors directly. We know its mass estimated from its brightness. We measured its acceleration using the thousands of observational data points collected from hundreds of observatories. The third factor. The gas ejection velocity is determined by thermodynamics. When ice sublimes, the resulting gas molecules have a characteristic speed that depends on temperature and molecular weight. For water vapor at the temperature 3I Atlas's surface would have reached at perihelion, this velocity is approximately 300 meters per second. This is not a guess. This is basic physics confirmed by laboratory experiments and observations of countless comets. Water molecules at a given temperature move at a certain speed, so we can solve for the missing variable. We know the acceleration, we know the gas velocity, we know the comet's mass. The equation tells us how much mass must have been lost. The answer is 13%. Minimum. 13% might not sound dramatic until you visualize what it means. Imagine a mountain 5 kilometers tall and 5 kilometers wide. Now imagine vaporizing 13% of that mountain, turning solid rock and ice directly into gas and flinging it into space. 5 billion tons of gas and dust do not disappear quietly. The gas expands, forming a cloud that initially moves radially outward at 300 meters per second. But then 2 forces act upon this cloud. The first is radiation pressure. Photons from the sun, despite being massless, carry momentum. When they strike dust grains or are absorbed by gas molecules, they transfer that momentum, pushing the material away from the sun. For small dust particles, this force can exceed the sun's gravitational pull. The second force is the solar wind, a continuous stream of charged particles flowing outward from the sun at speeds of 400 to 800 kilometers per second. When these particles interact with ions in the comet's coma, they create the straight ion tail that always points directly away from the sun. Both forces are unidirectional away from the sun. Both are continuous. Both are powerful. The result is unmistakable and has been observed in every active comet ever studied at tail. For 3I Atlas to lose 5 billion tons over a month means an average mass loss rate of roughly 2,000 tons per second. That's comparable to some of the most spectacular comets in recorded history. If 3I Atlas ejected that much material, the resulting cloud would be detectable not just with professional instruments, but potentially with good binoculars. The tail should be obvious to anyone who looked. Some have argued that perhaps the gas is there, but we simply cannot see it. Maybe it's too diffuse, spread too thin to be detected. This counter-argument seems reasonable until you examine it carefully. We successfully detected much smaller amounts of gas from 3I Atlas back in August using the James Webb Space Telescope. That detection was made when the object was at 2.8 astronomical units from the Sun, nearly 6 times farther than at perihelion. Webb detected carbon dioxide in the coma. If we could see a relatively small amount of gas from that great distance, it is implausible that we would completely miss a cloud containing billions of tons of freshly ejected material now. Moreover, we have the comparison with Comet Lemon. This ordinary comet displaying a clear tail is losing mass at a rate far lower than what 3I Atlas would need. Yet Lemon's tail is easily visible while 3I Atlas shows no comparable structure. The physics is unambiguous. The observations are clear. The two are irreconcilable if we assume 3I Atlas is a natural comet accelerating through outgassing. This brings us to the transverse component of the acceleration, the push perpendicular to the sun's direction. This is harder to explain with natural outgassing. Sunlight pushes directly away from the sun. Solar wind flows radially outward. For a comet to experience a sideways push, it would need asymmetric jets' active regions on its surface not pointed directly toward or away from the sun. This is possible, comets do have jets, but the magnitude of the transverse acceleration is substantial, suggesting either very powerful jets or jets oriented just right, and those jets should be visible. Again, we see nothing of the sort. Even if we allow for maximum uncertainty in all parameters, assuming the comet is larger than we think, assuming the outgassing is more efficient than typical, you still cannot get below about 10% mass loss. The numbers simply do not work while remaining consistent with known physics. This is not about sophisticated theories. This is basic physics taught in undergraduate courses. Force equals mass times acceleration. Momentum is conserved. These principles have been tested billions of times over 3 centuries. They have never been found to fail. If they are failing now, we need an extraordinary explanation. The more likely possibility is that they are not failing. Our interpretation is, we assumed 3I Atlas was accelerating due to natural cometary outgassing because that is what comets do. But if 3I Atlas is not behaving like a comet in its visible characteristics, no significant tail, no massive coma, perhaps it is because it is not accelerating like a comet.
The equation remains true. Momentum is conserved. Something must be expelled to produce the acceleration. But what if that something is not 5 billion tons of ice and dust moving at 300 meters per second? What if it is a much smaller amount of material moving at a much higher velocity? The thrust of a rocket depends on 2 factors: the mass flow rate and the exhaust velocity. The momentum change is the product of these 2 values. To produce the same thrust, you can expel a lot of material slowly or a small amount of material very quickly. Natural cometary outgassing is the former. Technology offers the latter. An ion drive, for example, accelerates ions to velocities of 30,000 to 50,000 meters per second, 100 times faster than natural sublimation. To produce the same thrust, an ion drive would need to expel 100 times less mass. Instead of 5 billion tons, it would need 50 million tons. That's still substantial, but it's a 2 orders of magnitude difference in detectability. 50 million tons of ionized gas expelled at high velocity might be difficult or impossible to detect with current instruments. This is speculation? Yes, but it is speculation grounded in physics we understand. We are not invoking magic. We are invoking rocket science, literally. The ancient mathematicians of Alexandria understood that the universe operated according to rational principles that could be described with geometry and number. When the mathematics tells us that a comet must have lost billions of tons of mass, and our eyes tell us there is no evidence of that mass loss, we face a moment of truth. Perhaps like the ancient astronomers who placed Earth at the center, we have placed the wrong assumption at the center. We have centered our model on the idea that all interstellar objects are natural. What if that assumption is hiding the truth? The equation does not lie. Momentum is conserved. The acceleration is real. The gas cloud that should exist does not. One of these statements must be wrong, or our understanding of what 3 Atlas is must change. When starlight passes through a prism, it separates into a rainbow, a spectrum. But this is not a uniform rainbow. There are dark lines and bright lines, gaps and peaks, a barcode written in light itself. These lines are the fingerprints of elements. Each chemical element, when heated or illuminated, emits or absorbs light at very specific wavelengths. Sodium produces 2 bright yellow lines. Hydrogen creates a series in the red, blue, green, and violet. Iron has thousands of lines scattered across the spectrum. Spectroscopy allows us to determine not just what distant objects look like, but what they are made of. We can perform chemistry experiments on stars billions of light years away.
When the Very Large Telescope in Chile turned its spectroscopic instruments toward 3I Atlas in August 2024, the scientists expected to see the familiar signatures of a comet. Water carbon dioxide cyanide compounds the standard constituents of cometary gas. What they saw instead made them pause and examine their data very carefully, checking for instrumental errors. They saw nickel. Metal emissions from comets are not entirely unknown. Comets do contain metals, elements incorporated into their structure from the primordial cloud that formed their parent star system. These metals are typically locked in mineral grains and only released when those grains are heated to very high temperatures. But the ratio of metals in 3I Atlas was profoundly wrong. In nature, nickel and iron are inseparable companions. They form together in the cores of massive stars. They are scattered together when those stars explode as supernovae. Everywhere we look in the cosmos, the ratio of iron to nickel is remarkably consistent. Approximately 20 iron atoms for every nickel atom. This ratio is not just common, it is essentially universal. We see it in meteorites, asteroids, Earth itself, our Sun, other stars, and previous comets including 2I Borisov. It is one of the most reliable chemical signatures in astrophysics. In 3I Atlas, the iron that should accompany the nickel was conspicuously absent, or at least present in far smaller amounts. The nickel-to-iron ratio was orders of magnitude away from any known natural object. The research team proposed a hypothesis. They suggested that the nickel might be in the form of nickel tetracarbonyl, a compound consisting of one nickel atom bonded to 4 carbon monoxide molecules. This is where the chemistry becomes fascinating and troubling in equal measure. Nickel tetracarbonyl is a real compound with well-understood properties.
It was discovered in 1890 by German chemist Ludwig Mond. The compound is highly volatile. It becomes a gas at very low temperatures, just 43 degrees Celsius. The Mond process works as follows. Impure nickel is exposed to carbon monoxide at moderate temperatures, forming gaseous nickel tetracarbonyl. This gas is then heated to about 200 degrees, causing it to decompose back into pure nickel metal and carbon monoxide. The result is nickel of exceptional purity. This process is used today in industrial settings to produce pure nickel for electronics, specialized alloys, and applications requiring high material purity. Here is the problem. Nickel tetracarbonyl is not known to form naturally in space. The conditions required are specific and do not typically occur in comets. Carbon monoxide is present in comets, but the formation of the carbonyl compound requires more than just the presence of constituents. The research team acknowledged this, noting that, under exotic conditions not yet observed, such compounds might form naturally. This is scientifically honest. They are not claiming to know for certain that natural formation is impossible. But we must be honest about what exotic conditions not yet observed means. It means we have no natural mechanism to propose. This is where Occam's razor becomes relevant, which is simpler, that 3I Atlas formed through unknown natural processes that created chemical compounds we have never seen naturally before, or that 3I Atlas is constructed from industrial-grade materials. If you were designing an interstellar probe, a vessel meant to function for millions of years in the harsh environment of space, what materials would you use? You would want materials that are strong, stable across vast temperature ranges, resistant to radiation damage, and capable of withstanding thermal shocks.
Nickel-based superalloys fit these criteria almost perfectly. They are used in Earth's most demanding applications: jet engines, rocket nozzles, nuclear reactors, and spacecraft components. If 3I Atlas were a manufactured object, the presence of nickel-rich alloys would make perfect engineering sense. And if that object were venting material either as propellant or through slow ablation by solar radiation, we would expect to detect nickel. We would not necessarily expect to see much iron if the original construction deliberately minimized iron content. The comparison with 2I Borisov is instructive. That previous interstellar comet displayed completely normal chemistry. Its nickel-to-iron ratio matched expectations. Its cyanide content was typical. In every chemical test, 2I Borisov looked like it could have been born in our own system. 3I Atlas is different. Its chemistry is anomalous in multiple independent measurements. Beyond the nickel without iron puzzle, there is the nickel-to-cyanide ratio. Comets are typically rich in cyanide compounds because these form readily in cold, carbon-rich environments. 2I Borisov had normal cyanide abundances. 3I Atlas has a nickel-to-cyanide ratio orders of magnitude higher than any known comet. There is simply too much nickel relative to cyanide. When Avi Loeb compiled his statistical analysis, he calculated that the probability of this chemistry occurring naturally is less than 1%, a greater than 3 sigma outlier. A single outlier can happen by chance. But when you have multiple independent outliers in the same object, the chemistry, the acceleration without a tail, the trajectory, the cumulative probability drops rapidly. There is also the matter of water content. Webb's spectroscopic observations revealed that the gas surrounding 3I Atlas is about 87% carbon dioxide, 9% carbon monoxide, and only 4% water. This is highly unusual. Most comets are dominated by water ice. They are often described as dirty snowballs. The low water content suggests 3I Atlas formed in an extremely cold environment far from its host star. But here is the tension metals like nickel require high temperatures to form. They are products of stellar nucleosynthesis forged in the cores of massive stars. They typically condense in the warmer inner regions of protoplanetary disks. So we have evidence that 3I Atlas formed in an extremely cold environment and evidence that it contains materials from high-temperature environments. These two lines of evidence point to different formation environments. A natural comet should tell a coherent story about where and how it formed. 3I Atlas tells two different stories simultaneously, unless it did not form through natural accretion at all. If it was constructed, then its composition would reflect choices made by engineers based on material properties, not the happenstance of chemical condensation. The geophysicist Stefan Burns offered another interpretation. Based on the missing tail, the resilience at perihelion, and the chemistry, he concluded that 3I Atlas is likely not a fluffy pile of ice and dust, but a fairly solid, dense object composed primarily of metal and carbon compounds. If the object is primarily metallic, with a surface coating of carbon-rich material, this would explain several observations: the nickel emissions, the lack of a massive tail, the survival of perihelion intact, the blue color shift. But again, this raises the question, where do solid, metal-rich bodies come from in the outer reaches of a planetary system where low water content suggests formation? In our solar system, metal-rich bodies are found in the inner asteroid belt close to the Sun.
The carbonaceous asteroids rich in volatiles are found in the outer belt. This reflects the temperature gradient in the early solar nebula. 3I Atlas's chemistry suggests a formation environment that was simultaneously very cold and capable of concentrating metals in an unusual way. We have no clear natural mechanism for this. The ancient alchemists sought to transmute lead into gold, to purify base metals into noble ones. They believed that with the right processes, such transformations were possible. They were wrong about the specifics, but right about the principle: materials can be refined through deliberate processes. The Mond process for nickel purification is a modern form of alchemy using chemistry to separate one metal from another to create materials that do not occur naturally in such purity. If we are seeing evidence of such purification in 3I Atlas, it points not to natural formation, but to processing, to deliberate manipulation of materials.
The chemistry of 3I Atlas is not just unusual, it is a collection of anomalies that do not form a coherent picture of natural formation. Each can perhaps be explained individually with sufficiently exotic hypotheses. But explaining them all simultaneously with a natural model requires us to stack unlikely scenarios upon one another. The alternative is uncomfortable but increasingly difficult to dismiss. Chemistry does not lie. The elements are what they are, regardless of how we interpret them. The question is not what we are seeing, but what it means. In the halls of power, in the offices where decisions are made about what the public should know and when they should know it, there exists a tension that most people never see. It is the tension between transparency and control, between the public's right to information and the institutional impulse to manage narratives. This tension became acute in the autumn of 2024 as 3I Atlas passed through the inner solar system. On July 31st, Representative Anna Paulina Luna from Florida's 13th District submitted a letter to NASA. It was not a casual inquiry. It was a detailed proposal to redirect the Juno spacecraft from its orbit around Jupiter to intercept 3I Atlas. The proposal suggested that a specific engine burn on September 14th could position Juno for a close encounter. The estimated cost, $15 million. By November, Luna's tone had shifted dramatically. Her second letter was not about planning future missions. It was a demand for data that NASA already possessed, but was refusing to share. The request was remarkably precise. Luna demanded the highest resolution images from the high-rise camera aboard the Mars Reconnaissance Orbiter taken on October 2nd and 3rd. These images were expected to have a resolution of 30 kilometers per pixel. She also requested any supplementary data from other Mars missions and all relevant observations from Parker's Solar Probe, Hubble, and Webb.
These are not vague requests. These are specific instruments, specific dates, and specific data sets that should exist if these missions were operating as planned. The timing of this shift tells you everything about what was likely happening behind the scenes. In July, Luna seemed optimistic about collaboration. By November, it appears she had concluded that NASA had been observing 3I Atlas extensively, but was withholding crucial findings. That is not speculation. It is the clear implication of her letter. NASA has the data. NASA is not releasing it. And now a member of Congress is formally demanding to know why. Avi Loeb sent his own request directly to Professor Alfred McEwen at the University of Arizona, the principal investigator for the high-rise camera team. As of the publication of his latest article, he had received no response. Think about that. The lead scientist on arguably the highest resolution camera that photographed 3I Atlas during its pivotal Mars flyby is not responding to inquiries from one of the most prominent astrophysicists in the world. This silence is deafening. The high-rise images are scientifically crucial. With a potential resolution of 30 kilometers per pixel, they would be approximately 3 times sharper than Hubble's best public image. For an object whose size is uncertain, whose surface properties are a complete mystery, that level of resolution could be transformative. The brightest pixel in the high-rise images would provide the best constraint yet on the actual physical size of the nucleus. We could finally determine if 3I Atlas is truly the 5-kilometer diameter solid object that some estimates suggest. We could look for surface features for active jets for any asymmetries. But we cannot do any of that without access to the images. The controversy exploded into mainstream consciousness in an unexpected way. Kim Kardashian tweeted at NASA administrator asking for clarification about 3I Atlas. Her tweet reached hundreds of millions of followers. The response was reassuring in tone but notably evasive in content. The administrator acknowledged it was a great question and stated that observations showed it was the third interstellar comet, but offered no new data and did not address the specific anomalies. Representative Luna's involvement represents something deeper than curiosity. Luna sits on committees with direct oversight authority over NASA. Her questions are not casual inquiries, they are formal congressional actions.
When a member of Congress demands that a federal agency release data collected with taxpayer dollars, it creates pressure that cannot be easily ignored. The government shutdown that began in October complicated everything. NASA's official website stopped updating. The usual channels for data release went dormant. The Public Affairs Office was shut down. This created a perfect storm of opacity, an information vacuum right when 3i Atlas was passing through its most scientifically interesting phase. Was the timing simply unfortunate, or was it convenient? That question is beyond our scope here, but the effect was undeniable. It prevented the normal flow of information. Despite the shutdown, some raw data continued to flow through automated systems. This is how we got those intriguing, though low-resolution images from the Perseverance rover on Mars. Astrophotographer Simeon Schmaus painstakingly stacked 20 images and found a faint object in Corona Borealis, very close to where 3i Atlas was predicted to be. Is it definitive? No, but it is suggestive. However, these are raw images from a camera designed to photograph rocks, not distant comets. The high-resolution, high-rise images remain locked away.
Multiple Mars orbiters had 3i Atlas in their sights. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter did photograph the object and released some images. They show fuzzy dots. 3i Atlas against stars, but these are from cameras designed for surface imaging, not distant objects. Their scientific value is limited. NASA's Mars Reconnaissance Orbiter possesses the high-rise camera built for exactly the kind of long-range, high-resolution imaging that could reveal crucial details. We know those images exist. They were taken when 3i Atlas was just 30 million kilometers from Mars. They are not being released. Why would NASA withhold scientific data about such a significant astronomical object? One benign possibility is that the images require extensive calibration and processing, and the shutdown interrupted that process. Another is that the images show something unexpected, something requiring careful analysis before release to avoid misinterpretation. Scientists generally prefer to understand their data before publishing it, especially when that data might generate significant public interest. A third possibility is that the images show something NASA does not want to discuss yet. This doesn't necessarily mean aliens or technology, but perhaps something that contradicts previous statements or reveals uncertainty where certainty was claimed. Bureaucracies do not like admitting they were wrong, and they especially do not like admitting uncertainty when they have previously projected confidence. This entire controversy highlights a fundamental tension. NASA is both a scientific organization and a government bureaucracy, and those two identities do not always align. Science demands transparency, immediate data release, and open debate. Bureaucracy demands careful messaging, controlled narratives, and avoiding statements that might need correction. When an object like 3i Atlas comes along, that tension becomes acute. Representative Luna's demand is essentially a demand that NASA prioritize its scientific identity over its bureaucratic one. The Mars Reconnaissance Orbiter cost $720 million to build and launch. Every dollar came from taxpayers. When that camera photographs something as significant as 3i Atlas, the resulting images are not NASA's private property. They are public data collected with public resources. The public has a right to see them. As we wait for the high-rise images, as we watch this bureaucratic standoff play out, 3i Atlas continues its journey. It does not care about politics or agency rivalries. It is simply moving, following its trajectory, either expelling gas we have not detected or using some other method. The very images that could help us understand which of those is true exist in a database somewhere ready to reveal their secrets. We cannot see them not because they do not exist, but because the people who control access have decided that now is not the time to share. In democratic societies, sunlight is said to be the best disinfectant.
Transparency is the foundation of trust. When institutions withhold information without clear justification, they breed exactly the kind of speculation and mistrust they claim to want to avoid. The silence from NASA is not just frustrating, it is in itself a kind of data. It tells us something about how uncomfortable this object makes those in positions of authority. What are they waiting for? What analysis are they conducting behind closed doors? And most importantly, what will they tell us when they finally speak? For 7 decades, we searched the skies for visitors from other star systems. We knew mathematically that such objects must exist. The violent formation of planetary systems should scatter debris into interstellar space. Gravitational interactions with giant planets should eject comets and asteroids. The galaxy should be filled with nomadic debris wandering between the stars. But knowing they exist and actually seeing one are different things. For thousands of years of recorded astronomy, we saw nothing. 0 confirmed interstellar objects. Our solar system appeared to be an island universe unto itself. Then, in 2017, Oumuamua shattered that isolation. For the first time in human history, we detected an object that was unambiguously from beyond our solar system. It was a moment of profound significance, though many failed to grasp it at the time. Oumuamua was strange in almost every measurable way. Its shape was extremely elongated, at least 5 times longer than it was wide, possibly 10 times. This made it unlike any asteroid or comet in our solar system. Its surface was unusually reflective, suggesting either ice or metal.
It was tumbling, chaotically rotating about multiple axes simultaneously. But the feature that generated the most controversy was its motion. As Oumuamua receded from the sun, careful measurements revealed it was accelerating beyond what gravity alone could explain. Something was pushing it. In the academic papers that followed, researchers proposed the natural explanation outgassing. Even though Oumuamua showed no visible coma or tail, perhaps it was venting a small amount of gas, just enough to create thrust, but too little to be detected. This explanation had problems. The amount of outgassing required to explain the acceleration should have been visible. Moreover, the acceleration continued for weeks, requiring a sustained release of volatiles that should have created at least some detectable signature. When Avi Loeb proposed that Oumuamua might be artificial, perhaps a light sail pushed by solar radiation, the response was swift and largely negative.
The idea was deemed too speculative, too sensational, too willing to leap to extraordinary conclusions based on limited data. Fair enough. One anomalous object does not prove anything. Oumuamua could be a nitrogen iceberg from Pluto-like worlds, as some suggested. It could be a hydrogen iceberg. It could be a completely new class of natural object we had never encountered. But then came 2I Borisov in 2019. This second confirmed interstellar visitor was in every way boringly normal. It looked like a comet. It acted like a comet. Its chemistry was typical. Its acceleration was fully explained by visible outgassing. It had a lovely tail that behaved exactly as expected. 2I Borisov was proof that most interstellar objects are probably just what we expect natural debris. It suggested that Oumuamua might be an outlier, unusual but still natural, and now we have 3I Atlas. Once is an anomaly, twice is a coincidence, 3 times is a pattern. Here is the pattern of the first 3 interstellar objects ever detected passing through our solar system. 2 of them, Oumuamua and 3I Atlas, exhibited the exact same inexplicable characteristic. Both showed non-gravitational acceleration without a visible cometary tail to explain it. This is no longer a single isolated event. We now have multiple data points. The odds of this happening by chance, if these objects are drawn from a random population of natural interstellar debris, are vanishingly small. It suggests that objects with this particular anomalous property might actually be common in the interstellar medium. So what does this pattern mean?
One possibility is that there is a class of natural interstellar objects that behave this way, and we simply do not have a theory for them yet. Perhaps they are composed of materials that sublime invisibly. Perhaps they have properties we have not imagined. Science is always open to discovering new natural phenomena.
We should not assume we know everything about how the universe works, but there is another possibility. What if we are not seeing a class of natural objects, but a class of technological ones? What if Oumuamua and Three-Eye Atlas are related? Not necessarily from the same civilization, but perhaps examples of a common type of technology used for interstellar exploration probes, designed to be efficient, resilient, and perhaps deliberately difficult to identify as artificial. Oumuamua, being much smaller and faster, could have been a scout, a flyby mission designed for rapid reconnaissance. Three-Eye Atlas, being 1,000,000 times more massive and moving more slowly through our system, could be something different: an orbiter, a long-term observatory, or even a mothership. The trajectory of Three-Eye Atlas with its multiple planetary flybys is much more consistent with a detailed survey mission than Oumuamua's simple hyperbolic path. It is almost as if Oumuamua was the quick look and Three-Eye Atlas is the follow-up. This is speculation, but it is speculation grounded in the pattern we observe. When you have two data points that share the same inexplicable feature, you are no longer dealing with an anomaly. You are dealing with a category. The defining characteristic of this new category is that they behave as if they are propelled. Consider the implications. If just 2 out of 3 interstellar objects show this characteristic, and if our detection methods are biased toward finding smaller, slower objects, first, then the actual population of accelerating interstellar objects might be far higher than we think. We might live in a galaxy where technological artifacts are common, where the space between stars is filled not just with natural debris, but with ancient probes, defunct vessels, autonomous explorers sent out millions of years ago by civilizations that may no longer exist. This idea has a name in the scientific literature: the interstellar archaeology hypothesis. It suggests that the first evidence of extraterrestrial intelligence we find might not be a radio signal or an exoplanet with an artificial atmosphere. It might be an artifact passing through our own solar system mistaken for a comet until someone looks closely enough. The pattern of Oumuamua and Three-Eye Atlas fitting this hypothesis is remarkable. But patterns can deceive. The human mind is prone to seeing connections where none exist, to finding meaning in randomness. This is why the December observations are so critical. They will tell us whether the pattern is real or illusory. If Webb finds the missing gas cloud around Three-Eye Atlas, then the pattern breaks. We are back to having one anomalous object out of 3, and the natural explanation remains viable. But if Webb confirms the absence of the gas cloud, then the pattern strengthens. We will have 2 confirmed objects out of the first 3 detected that cannot be explained by natural processes using our current understanding. At that point, the conversation must change. We can no longer dismiss the technological hypothesis as wild speculation. It becomes the simplest explanation for the observations. The ancient Greek philosopher Thales taught his students to look for natural explanations for natural phenomena. He rejected supernatural interpretations of the world. He believed that reason and observation could reveal truth. But Thales also taught his students to follow the evidence even when it led to uncomfortable conclusions. The evidence of Oumuamua and Three-Eye Atlas is leading us to an uncomfortable place. We are approaching a moment where we must decide: do we follow the evidence or do we cling to comfortable assumptions? The pattern is there, visible to anyone willing to look.
What we choose to see in that pattern will define not just our understanding of these objects, but our readiness to accept that we might not be alone. Let us venture into speculation, but speculation grounded in physics we understand. If Three-Eye Atlas is not accelerating through natural outgassing, then something else is producing thrust. What could that be? The most straightforward technological explanation is a form of electric propulsion. Modern spacecraft use ion drives engines that accelerate charged particles to very high speeds using electric or magnetic fields. The Dawn spacecraft, which explored the asteroids, Vesta and Ceres used an ion drive powered by solar panels. It worked by ionizing xenon gas and accelerating the ions through an electric field to speeds of about 40,000 meters per second. Compare that to the 300 meters per second of natural cometary sublimation. An ion drive is more than 100 times more efficient in terms of exhaust velocity. This means that to produce the same thrust, you need to expel 100 times less mass. For 3I Atlas, this would reduce the required mass loss from 5 billion tons to 50 million tons. That is still substantial, but it is a difference of 2 orders of magnitude in terms of detectability. 50 million tons of ionized xenon or argon expelled at high velocity might be extremely difficult or impossible to detect with current instruments. The exhaust from an ion drive is nearly invisible. The ions are moving so fast they do not emit much light. The exhaust plume is transparent. You could be looking directly at an operating ion drive and see almost nothing. This is not science fiction. This is technology we have already developed and deployed. An interstellar civilization with millions or billions of years of technological development would have far more advanced versions of the same basic concept. Another possibility is a solar sail. A solar sail is an enormous, ultra-thin reflective surface. Photons from the sun, though massless, carry momentum. When they bounce off the sail, they impart a tiny push. Over time, this push can accelerate a spacecraft to high speeds without requiring any onboard fuel. The acceleration from a solar sail is purely radial, directly away from the sun. This matches one component of 3I Atlas's observed acceleration. However, 3I Atlas also showed a transverse component perpendicular to the sun's direction. A simple flat sail cannot produce this, but an active sail could. Imagine a sail that can change its shape or angle, or that has reflective vanes that can be oriented to redirect thrust. Such a system could produce acceleration in any direction by carefully controlling how sunlight reflects off different sections. The strange brightening and blue color shift 3I Atlas exhibited near Perihelion could be interpreted as evidence of a light manipulating surface. When a reflective surface is angled toward you, it appears brighter. When it tilts away, it dims. The observed brightness variations might not be natural outgassing at all, they might be geometric effects from a rotating sail or similar structure. This is highly speculative, but it fits the observations better than any purely natural explanation currently proposed. We can also consider more exotic possibilities. A fusion rocket would use nuclear fusion to heat propellant to extreme temperatures and expel it at enormous speeds. The exhaust would be a plume of superheated plasma. Depending on its composition and density, this might be detectable or might be too diffuse to see. The most exotic possibility existing at the edge of theoretical physics is that 3I Atlas might not be using a reaction drive at all. Some physicists have speculated that sufficiently advanced technology might manipulate space-time itself, creating local distortions that move an object without requiring mass ejection. This is purely theoretical. We have no idea if such technology is even possible, much less practical. But if it exists, it could explain any kind of acceleration without any visible exhaust whatsoever. We do not need to resort to such exotic speculation. A powerful ion drive. A technology we already understand and use is sufficient to explain the primary anomaly. The nickel without iron chemistry could be explained by the use of nickel-rich alloys in construction. The on and off nature of the acceleration could be the drive firing for course corrections and then shutting down. The pieces fit into a coherent picture. This brings us to the anti-tail observed in July and August. Adam Hibbard, a colleague of Avi Loeb, pointed out something fascinating.
If 3i Atlas were a spacecraft slowing down using forward-facing thrusters, this is exactly what we would expect to see. The anti-tail would be the exhaust plume from a braking maneuver. As 3i Atlas approached perihelion, that anti-tail diminished. This is consistent with the spacecraft completing its deceleration, achieving its desired trajectory, and shutting off the forward thrusters. The arrival geometry supports this interpretation. The probability that a random interstellar trajectory would bring an object close to Mars, Venus, and Jupiter, all while being hidden from Earth during perihelion, is about 1 in 20,000. When combined with the 1 in 500 probability of its ecliptic alignment, the odds drop to about 1 in 10 million. At that point, the trajectory starts to look less like coincidence and more like intentional targeting. If you wanted to design an interstellar mission to survey our solar system, this is exactly how you would do it.
You would aim for the ecliptic plane where the planets are. You would time your arrival for multiple planetary flybys. You would use the sun for a gravity assist, and you might do all of this while minimizing visibility from the most technologically advanced planet. The mission profile that makes perfect sense for an intelligent probe happens to match what 3i Atlas actually did. Why has it not communicated with us? There are many possible reasons. It might not be designed to. It might be communicating in ways we cannot detect. It might be malfunctioning. Or, and this is profound to consider, it might be deliberately avoiding communication. An advanced civilization might program its probes to observe emerging civilizations without interfering, following a non-contact directive. A probe following that rule would look exactly as 3i Atlas appears to look, collecting data, adjusting its trajectory for optimal observation, but remaining silent. This hypothesis is falsifiable, which is crucial for scientific credibility. If the December observations from Webb show the massive gas cloud required by natural sublimation, then this hypothesis is wrong. The data will force us to accept the natural explanation. But if the gas cloud is not there, if the anomalies remain, then we must take the alternative seriously. The discomfort is understandable. Accepting that 3i Atlas might be a probe means accepting that we are not alone, that other civilizations exist with technology capable of interstellar travel, and that one of their artifacts is currently passing through our solar system. But discomfort is not a reason to reject a hypothesis if it is where the evidence leads. The ancient Romans had a saying, astra inclinant sed non obligant. The stars incline us but do not bind us. They understood that cosmic forces influence but do not determine. Perhaps we are now learning a corollary: the cosmos contains more than stars. It might contain emissaries, watchers, probes sent by minds that looked up at their own skies and wondered what lay beyond. The propulsion system hypothesis remains on the table, neither proven nor disproven, but increasingly difficult to ignore. Walk with me for a moment into the past. Not the recent past of telescopes and spacecraft, but the deep past of naked-eye astronomy, when humans first looked up and tried to make sense of the wandering lights above. The Babylonians 5,000 years ago kept meticulous records of celestial phenomena. They tracked the motions of planets, with remarkable precision predicted eclipses, and recorded the appearances of comets. They called comets hairy stars and viewed them with a mixture of awe and dread. In their clay tablets preserved by accident in the ruins of ancient libraries, we find detailed descriptions of comets, categorized by the number of tails, their colors, and their paths across the sky. Some comets were seen as good omens, others as harbingers of disaster. Kings would consult astronomer priests to interpret these signs. We smile at this, now dismissing it as superstition. But buried in that ancient practice is something profound, the recognition that the heavens are not static, that they contain visitors, anomalies, things that do not fit the regular pattern. The Chinese were even more systematic. For over 2 millennia, Chinese astronomers recorded every comet visible to the naked eye. The Book of Silk.
A text from the 2nd century BCE contains descriptions of 29 different comet types classified by their appearance and behavior, the comprehensive mirror to aid in government. Compiled in the 11th century CE catalogs, hundreds of cometary appearances with dates, durations, and sky positions. What is remarkable about these records is their objectivity. Unlike the Babylonian interpretations which focused on omens, the Chinese records are largely descriptive. They tell us what was seen when and for how long. They are data, and in all of these thousands of years of meticulous observation, there is no record of a comet that accelerated without a visible tail. Every comet described has the characteristic features: a head, a coma, and at least one tail. The tails always point away from the sun. This is so consistent that it became one of the defining features of what a comet is. When Tycho Brahe proved in 1577 that comets were celestial objects beyond the moon, he did so using parallax measurements from different locations on Earth. His work was revolutionary, overturning centuries of Aristotelian dogma, but even Tycho's comets behaved as expected. They had tails. They followed predictable paths. The Maya in Mesoamerica also tracked celestial phenomena with remarkable precision.
Their astronomical observations were woven into their architecture, their calendar systems, their mythology. They could predict Venus's appearances with accuracy that would not be surpassed in Europe for centuries. The Maya believed the sky was populated by God's ancestors and cosmic forces that influenced earthly affairs. But beneath the mythological interpretation was careful observation. They knew that celestial events followed patterns, that these patterns could be understood and predicted. What would these ancient astronomers have made of Three-Eye Atlas, a visitor from beyond, accelerating, without a tail arriving, with a trajectory that seems almost deliberate? The Babylonians might have called it a sign of a new age, the arrival of forces beyond human comprehension. The Chinese would have recorded it meticulously, noting every detail, seeking patterns and precedents. The Maya might have seen it as a manifestation of cosmic cycles, a return of something ancient. We, with our modern instruments and our scientific framework, are faced with the same fundamental challenge those ancient observers faced: how to interpret something that does not fit our categories. There is a danger in both directions. We can be too quick to invoke the extraordinary, seeing signs and wonders where none exist, or we can be too quick to dismiss the extraordinary, forcing anomalies into familiar categories because we are uncomfortable with ambiguity. The ancient astronomers, for all their limitations, had one advantage over us: they were comfortable with mystery. They did not expect to fully understand the cosmos. They observed, they recorded, and they remained open to the possibility that the universe contained things beyond their knowledge. We have lost some of that humility. Modern science has been so successful, has explained so much, that we sometimes forget how much remains unknown. We assume that anything we observe must fit into our existing framework, must be explicable by known processes. Three-Eye Atlas is teaching us, as the sky has taught humans for millennia, that the universe is under no obligation to conform to our expectations. The Sumerians, perhaps the first civilization to develop writing, described in their myths a time when the gods came down from the sky. We interpret this as mythology, as primitive explanations for natural phenomena or distorted memories of ancient rulers. But what if some of those myths preserve in garbled form genuine encounters with something from beyond? What if humanity has been visited before, in our deep past, by probes or travelers from other star systems? What if we simply lacked the conceptual framework to understand what we were seeing, and so recorded it as myth? This is the domain of speculation, of course, but it is speculation that becomes slightly less wild when we have objects like Three-Eye Atlas passing through our solar system, objects that behave in ways that natural processes struggle to explain. The point is not that ancient myths are literally true. The point is that the universe is vast, old, and likely filled with civilizations at various stages of development.
Some of those civilizations, having existed for millions of years longer than ours, might have sent out explorers long ago. Those explorers might still be out there wandering the galaxy, observing star systems, collecting data, and perhaps occasionally being glimpsed by beings who lack the technology to truly understand what they are seeing. We are now, perhaps for the first time in human history, in a position where we have both the instruments to detect such visitors and the knowledge to recognize them for what they might be. The ancient astronomers saw the same sky we do, but through different eyes. They did not have our telescopes, our mathematical models, our physical theories, but they had curiosity, patience, and an openness to wonder. As we stand at this moment of potential discovery, we could learn from them. We could approach 3i Atlas with the careful observation of the Chinese astronomers, the systematic categorization of the Babylonians, the geometric precision of the Maya, and the philosophical openness of the Greeks. We could observe, record, analyze, and remain humble in the face of mystery. The sky has always held mysteries. 3i Atlas reminds us that some of those mysteries might not be natural phenomena at all, but visitors. And if they are visitors, then we are no longer alone in our observations. We are being observed in return. That is a thought that would have resonated deeply with those ancient watchers of the skies. In science, we value precision. We want to quantify, to measure, to assign numbers to phenomena so we can compare them objectively. This impulse led Avi Loeb to create what he calls a ranking system for interstellar objects, a scale from 0 to 10 that attempts to quantify how likely an object is to be artificial rather than natural. A score of 0 means the object is definitively natural, fully explicable by conventional astrophysics. A score of 10 means it is definitively technological, with unambiguous evidence of design and manufacture. Most objects score a 0. Regular asteroids and comets, planets, stars, these are clearly natural. 2i Borisov. The second interstellar visitor scored a 1. It was overwhelmingly consistent with being a natural object, with perhaps 1 or 2 mildly unusual features that were nonetheless within the range of natural variation. Oumuamua scored much higher, around 6 or 7. Its extreme shape, its tumbling motion, and especially its acceleration, without visible outgassing, pushed it high up the scale into territory where natural and artificial explanations compete roughly equally.
3i Atlas currently ranks at a 4. That places it in the middle ground, more anomalous than 2i Borisov, less mysterious than Oumuamua, but definitely strange enough to warrant serious investigation beyond casual observation. A ranking of 4 means we can no longer dismiss the artificial hypothesis without addressing specific observations that do not fit natural models. This ranking is not based on a single feature, but on the cumulative weight of multiple documented anomalies. Let me walk you through them. Anomaly 1, trajectory alignment. 3i Atlas follows a retrograde orbit aligned to within 5 degrees of the ecliptic plane. For an object arriving from a random direction in the galaxy, the probability of being this closely aligned by pure chance is about 1 in 500. Anomaly 2, the sunward jet. During July and August 3s, Atlas displayed an anti-tail, a jet of material pointing toward the sun. This is extremely difficult to explain with standard cometary physics.
Anomaly 3, mass and speed. The nucleus is roughly 1,000,000 times more massive than Oumuamua, and it is moving faster through the galaxy. The probability of us detecting an object this large and fast so early in our search is less than 0.1%. Our surveys are biased to find smaller, slower objects first. Anomaly 4, arrival timing and geometry. 3i Atlas achieved close passes to Mars, Venus, and Jupiter, all while being unobservable from Earth during perihelion. The probability of this specific geometry is about 1 in 20,000. Anomaly 5, anomalous chemistry. The gas plume contains nickel without corresponding iron, and the nickel-to-cyanide ratio is orders of magnitude higher than any known comet. Probability below 1%. Anomaly 6, low water content. 3I Atlas contains only about 4% water, far lower than typical comets. Anomaly 7. Extreme negative polarization.
The light reflecting off 3I Atlas exhibits polarization properties never before seen in any comet. Anomaly 8. Brightening and blue color. Near Perihelion, 3I Atlas brightened and shifted toward blue wavelengths unexpected for a dusty object. Anomaly 9. Acceleration without a corresponding gas cloud. The measured acceleration requires massive mass loss, but observations show no evidence of the enormous gas cloud this should have produced. Anomaly 10. Lack of a tail post-perihelion. It survived extreme solar heating and a direct CME impact without producing the spectacular tail these processes should have created. Now here's the critical point. It is not about any single anomaly being impossible to explain naturally. You can probably construct a convoluted natural explanation for almost any one of them in isolation. The problem is explaining all 10 simultaneously with a single coherent natural model. At some point, the accumulated unlikelihood of the natural explanation may be surpassed by the simpler, if extraordinary, artificial explanation. This is Occam's razor. The simplest explanation that accounts for all the observations should be preferred. A ranking of 4 is not a conclusion. It is an assessment of where we are based on current data. As more observations come in, that ranking could move. If the December observations show a massive gas cloud, the ranking will drop. If they confirm the absence, the ranking will climb, possibly into territory where the artificial hypothesis becomes more likely. The scale is dynamic. It forces us to continuously evaluate what the data is telling us, rather than locking into a position based on our prior assumptions. 3I Atlas sits suspended in that uncomfortable space where neither explanation is fully satisfying. The data pushes us away from conventional interpretations, but does not yet give us enough to fully embrace unconventional ones. But it is moving. With each observation that fails to fit the natural model, with each new anomaly added to the list, the object climbs the scale. It is approaching the point where we will need to make a choice about which explanation requires fewer assumptions. The ancient Greek philosopher Epicurus taught that when multiple explanations are possible, we should not arbitrarily prefer one over another without evidence. All hypotheses consistent with the data should be entertained until the evidence allows us to eliminate some of them. We are in an Epicurean moment with 3I Atlas. Multiple hypotheses remain on the table. The natural comet hypothesis is still alive, but it is increasingly burdened with the need to invoke multiple unlikely circumstances. The technological hypothesis requires us to accept something profound about the universe, but it explains the observations more simply. The December observations will not necessarily resolve this. Even if Webb finds no massive gas cloud, some will argue for ever more exotic natural explanations. And if Webb does find the gas cloud, some will argue it is not quite enough to explain the full acceleration. Science is rarely as clean as we would like. Rarely does a single observation definitively prove or disprove a hypothesis. More often we accumulate evidence gradually, and at some point a consensus emerges. The ranking scale attempts to make that process more explicit, more quantitative. It asks, given all the evidence, where does this object fall on the spectrum from clearly natural to clearly artificial? 3I Atlas at a 4 is in the zone of deep uncertainty. It is the zone where scientists should be most active, most curious, most willing to challenge their own assumptions. It is also the zone where institutional resistance is strongest, where the pressure to conform to conventional explanations is most intense.
Because a ranking of 4 implies that we might need to take seriously an idea that until very recently was considered beyond the pale of respectable science. The question is no longer, could this be artificial? The question is, how much more evidence do we need before we seriously consider that it might be? And that is a very different question. On December 19, 2024, Three-Eye Atlas will make its closest approach to Earth, coming within 269 million kilometers. By cosmic standards, that is remarkably close for an interstellar object, close enough for our most powerful telescopes to achieve unprecedented resolution and sensitivity. That date will either resolve this profound mystery or deepen it beyond anything we have seen. Every major observatory on the planet will be pointed at Three-Eye Atlas that week. This will be a full-court press, the astronomical equivalent of throwing every resource we have at a single target. The observations from the James Webb Space Telescope are the most critical. Its near-infrared spectrograph can measure the composition of the coma with exquisite precision. It will tell us exactly what is in that gas cloud and how much of it there is. The data from Webb will not be ambiguous. It will not leave room for hand-waving or appeals to uncertainty. We will know. The key question Webb will answer is whether the mass of the gas surrounding Three-Eye Atlas is consistent with that 13% mass loss required by its acceleration. If Webb measures the gas mass and finds billions of tons of material present, the natural comet hypothesis survives. If Webb finds orders of magnitude less gas, the hypothesis fails. It is a simple binary outcome. The gas is there or it is not. There is a possibility that makes many people uncomfortable, but it must be considered.
What if Webb finds almost no gas? What if the coma it detects is similar to the modest one we saw back in August, with no evidence of massive recent outgassing? At that point, we would have a fundamental contradiction. The acceleration requires mass loss. The mass loss must produce a detectable gas cloud, but the gas cloud is not there. Something in that chain of reasoning must be wrong, and the most likely candidate would be the assumption that the acceleration was caused by natural sublimation. December 19th is also crucial for studying the object's rotation. Natural comets are usually in chaotic rotation, tumbling end over end. If Three-Eye Atlas shows stable rotation around a single axis, that would be highly unusual for a natural object but perfectly expected for a designed artifact. We will also be searching for any radio emissions. SETI organizations have been monitoring Three-Eye Atlas since its discovery, and this close approach is our best chance to detect any artificial signals. The most likely outcome is that the December observations will either confirm or refute the natural comet hypothesis based on the mass of the gas cloud. That single measurement is the linchpin. Everything else will provide supporting evidence. Avi Loeb has stated repeatedly that he will accept whatever the data shows. This is the scientific method in action. You propose hypotheses, you test them, and you update your beliefs based on evidence. Ego has no place in this process. Only the data matters. The window for these critical observations will last about 6 weeks. In that time, we will gather more data on this object than we have for any previous interstellar visitor. We will push our instruments to their absolute limits, and we will answer questions that have been accumulating since a telescope in Chile first spotted an object that would challenge everything we thought we knew. There is also the JUICE spacecraft data currently stored in onboard memory awaiting transmission to Earth in February. JUICE observed Three-Eye Atlas from the side, a vantage point impossible from Earth. Its sub-millimeter wave instrument will provide an independent measurement of water content. Its Janus camera will show us the morphology from a 90-degree angle. From Earth, it is difficult to distinguish the shape of a coma from a tail pointing directly away from us. From the side, JUICE will see the object in profile. It will see unambiguously whether there is a tail streaming out behind Three-Eye Atlas. If Earth-based images show no tail, and JUICE's images show no tail from the side, it would be decisive. The JUICE data is our independent verification, our crucial second opinion. There is also the possibility of using radar. NASA's Goldstone Solar System radar in California has the power to send a beam to Three-Eye Atlas and detect the echo. A radar observation would tell us about the nucleus itself. The way radar waves reflect depends on what the surface is made of.
A porous, icy rubble pile would return a weak, diffuse signal. A solid, metallic surface would return a strong, sharp echo. A successful radar detection could, in a single observation, tell us if the core of 3I Atlas is solid and whether it is rich in metals. If 3I Atlas returns a radar signature indicating a smooth, metallic, rapidly rotating object, the debate would be over. That is simply not a combination of properties that occurs in nature. The challenge is the immense distance, but during the December close approach, it might just be possible. Ultimately, the story of 3I Atlas is about more than just one strange object. It is about how science works at its best, and sometimes at its most frustrating. An anomaly like 3I Atlas is the greatest gift the universe can give to science. It is a puzzle that stretches our theories to their breaking point. It forces us to question assumptions, to build better instruments, and to imagine possibilities we had never considered. Regardless of whether 3I Atlas turns out to be a comet, a probe, or something in between that we do not even have a name for, yet the process of studying it will leave us richer. We will have pushed our telescopes to their limits. We will have developed new analysis methods. We will have engaged in a global conversation about our place in the cosmos. And we will have been reminded that the universe is under no obligation to conform to our expectations. The final chapter of this story has not yet been written. It will be written in the data that flows back from our robotic emissaries in the cold darkness of space. It will be written in debates and discussions in university halls and online forums. And it will be written in the hearts and minds of every person who looks up at the night sky and wonders with newfound urgency and awe if we are truly alone. December 19th is the date, the final test, the moment when we will learn whether our comfortable understanding of the cosmos is fundamentally correct, or whether we need to expand our conception of what is possible. The universe waits patiently. The telescopes are ready. Soon we will know. What happens if we are wrong? There are two ways we could be wrong about 3I Atlas, and the implications of each are profound. We could be wrong in thinking it is a natural object when it is actually technological. Or we could be wrong in suspecting it might be technological when it is actually just an exotic but natural object. Both errors carry serious consequences for how we approach the search for life in the universe. Let us start with the first scenario. Suppose 3I Atlas is indeed a probe and artifact from another civilization, and we fail to recognize it as such. Suppose we dismiss the anomalies, explain them away, and let this object pass through our solar system and leave without ever confirming what it actually was. What have we lost? We have lost a once-in-a-civilization opportunity to study extraterrestrial technology up close. 3I Atlas is here now. It is accessible. We could potentially send a mission to intercept it, but that opportunity exists for a very limited time. But the loss goes far beyond just this one object. If we fail here, we establish a pattern of dismissing evidence because it does not fit comfortable narratives. 3I Atlas will not be the last interstellar object we detect. Our survey capabilities are improving dramatically. More will come. If we develop a habit of explaining away anomalies rather than investigating them rigorously, we risk missing first contact, not because the evidence was not there, but because we refuse to look at it honestly. Now consider the second scenario.
Suppose 3I Atlas is natural, and we invest significant resources investigating it under the assumption that it might be technological. Suppose the December observations resolve all the mysteries and confirm it is just a weird comet. What have we lost? Honestly, not much. We would have conducted a thorough, multi-wavelength observational campaign on an interstellar object, gathering priceless data that advances our understanding of comets and star system formation. Even if the technological hypothesis is wrong, the science we do to test it is incredibly valuable. The asymmetry here is striking. If we treat 3I Atlas as possibly technological, and we are right, we make the single greatest discovery in human history. If we treat it as possibly technological and we are wrong, we still do excellent science. But if we assume it is natural and we are wrong about that, we lose a historic opportunity that may not come again in our lifetimes. The risk-reward calculation overwhelmingly favors investigation. This is a version of Pascal's wager applied to astrobiology. The potential payoff for being right is so immense that it justifies the modest cost of investigation, even if the probability of success is low. There is a deeper philosophical point here. For centuries, we have been learning that humanity is not special, that we are not the center of the universe. Copernicus showed that Earth orbits the sun, not the other way around. Galileo showed that planets are worlds, not perfect ethereal spheres. Darwin showed that humans evolved, we were not specially created. Yet in one area, we still cling to the assumption that we are unique. We assume we are alone. This assumption has no empirical basis. We know that planets are common. We know that the chemical ingredients for life are ubiquitous. We know that the universe is vast and ancient. The assumption that Earth is the only place where life developed, and especially the assumption that we are the only technological civilization, is not based on evidence. It is based on the absence of evidence, which is not the same thing. 3i Atlas challenges this final bastion of human exceptionalism. It forces us to move the search for extraterrestrial intelligence from the realm of abstract radio searches into the practical observational study of physical artifacts. Maybe we have been looking in the wrong place. Maybe first contact will not come through a message beamed across light years, but through an artifact that visits us. An artifact that can be photographed, studied, and perhaps one day even touched. Maybe that artifact is already here, has been here since July, and is preparing to leave in just a few months unless we act decisively. What happens if we are wrong? If we underestimate 3i Atlas, we may miss our moment in history. If we overestimate it, we do good science and remain humble about the limits of our knowledge. The asymmetry is clear. The choice should be obvious. But in the real world of science, it rarely is. The history of discovery is filled with moments where the data pointed toward a revolutionary new idea, but the scientific establishment, comfortable in its existing paradigms, resisted. Galileo was placed under house arrest for suggesting the Earth revolved around the sun. Alfred Wegener was ridiculed for his theory of continental drift. The idea that meteorites were rocks from space was once considered absurd. In each case, the evidence was there, but the intellectual and institutional inertia was too great to overcome without a prolonged fight. We are at such a moment now. The easy path, the safe path for a scientist's career is to assume 3i Atlas is natural. You can publish papers proposing exotic but natural explanations. You will get peer-reviewed, funded, and not labeled as a fringe thinker. The difficult path is to follow the data wherever it leads, even if it leads to a conclusion that challenges fundamental assumptions. Why is there such resistance to even considering the possibility of extraterrestrial technology? Part of it is healthy scientific skepticism. Extraordinary claims require extraordinary evidence, but part of it is something deeper. It is a kind of psychological defense mechanism. The confirmation that we are not alone would not just be a scientific discovery. It would be a cultural, philosophical, and religious event of unparalleled magnitude. It would force a reevaluation of humanity's place in the cosmos. It would be destabilizing. For some, the implications are so profound that it is psychologically easier to find any reason to dismiss the evidence rather than confront what it might mean. This is the human drama playing out behind the scenes. It is a conflict between caution and curiosity, between protecting the established order and venturing into the unknown. The silence from many mainstream institutions is not necessarily a conspiracy. It is more likely a sign of deep institutional caution. No one wants to be the official who cries aliens only to be proven wrong. The professional embarrassment would be immense.
But the cost of being wrong in the other direction of crying comet when an alien probe is sailing past is infinitely greater. This is why the December data is so critical. It has the power to cut through the debate, the caution, and the fear. The James Webb Space Telescope does not have a career to protect. It does not have philosophical biases. It is a machine for gathering light and turning it into data. It will measure the gas cloud or the lack thereof with cold, impartial precision. And at that point, the debate will be forced to shift from what we believe to what we know. The data will either provide a safe harbor for the natural explanation, or it will push us out into deep, uncharted waters. Let us venture into those waters for a moment. Let us assume the December observations confirm our suspicions. The acceleration is real, but the massive gas cloud is not there. What kind of propulsion system could achieve this? This is not just science fiction. It is a question of applied physics. We already discussed ion drives, but there are implications beyond just the technology. If 3I Atlas is using propulsion, then it is going somewhere, or at least it went somewhere, deliberately in the past. The trajectory with its multiple planetary flybys suggests reconnaissance. It suggests a survey mission. What would such a mission be collecting data about? Perhaps the most profound implication is this: if 3I Atlas is artificial, it means we are being observed. Not in a paranoid sense, but in a straightforward one.
A probe's purpose is to collect information about a target system. If 3I Atlas is a probe, then information about our solar system, including about Earth, is being recorded. That data might be stored locally, waiting to be retrieved. Or it might have already been transmitted traveling at light speed towards some distant star system where it will arrive centuries or millennia from now. Or perhaps it is being monitored in real time if the probe is part of a network. This is the true implication of the technological hypothesis. It is not just that intelligent life exists elsewhere. It is that it might be present here now, watching us as we struggle to understand what we are seeing. We live in a moment of profound transition. We are moving from a civilization that was isolated, unaware of any other intelligences, to one that might be part of a cosmic community. That transition is not abstract. It is not in the distant future. It might be happening now through our encounter with 3I Atlas. The choice is ours. We can approach this moment with courage, curiosity, and openness. Or we can retreat into comfortable assumptions, dismissing what we cannot easily explain. History will judge us not by whether we were right about 3I Atlas, but by whether we were brave enough to honestly investigate the possibility that we might be wrong about our place in the universe. We are suspended now in a strange liminal space, between question and answer, between hypothesis and verification. The December observations will come. The data will arrive. But until then, we wait. Waiting is difficult. The human mind craves resolution. We want answers, conclusions, certainty. Ambiguity is uncomfortable. It creates cognitive dissonance, a tension between competing interpretations of the same data. But science at its frontier is always ambiguous. The cutting edge of knowledge is where uncertainty lives. It is where competing hypotheses clash, where evidence is incomplete, where reasonable people can disagree. 3I Atlas has brought us to that frontier. It has given us a puzzle without a clear solution date that fits uncomfortably in our existing categories. How should we approach this uncertainty? There are several temptations to avoid. The first temptation is premature certainty, to declare before the December data arrives that we already know what 3I Atlas is. Some are certain it is a natural comet and explain away each anomaly with increasingly elaborate scenarios. Others are certain it is artificial and interpret every observation through that lens. Both forms of premature certainty are unscientific. They place belief before evidence. The honest answer right now is that we do not know. We have hypotheses, we have data, but we do not yet have enough to conclusively determine which hypothesis is correct. The second temptation is dismissive skepticism.
To assume that any unconventional explanation must be wrong simply because it is unconventional. This is not the same as healthy skepticism, which demands evidence before accepting claims. Dismissive skepticism refuses to seriously consider evidence because it challenges prior beliefs. The third temptation is sensationalism. To overstate the evidence, to claim certainty where none exists, to generate excitement through exaggeration, rather than through honest presentation of what we know and what we don't. The path between these temptations is narrow. It requires intellectual honesty, humility, and patience. We can acknowledge that the natural comet hypothesis is struggling to explain all the observations. We can acknowledge that the technological hypothesis, while extraordinary, is consistent with the data. We can hold both possibilities in mind simultaneously without committing prematurely to either. This is uncomfortable. The mind wants to choose, but choosing before we have sufficient evidence is not wisdom, it is wishful thinking. The ancient Stoic philosophers taught a practice called suspending judgment, epoche in Greek. It is the discipline of recognizing when you do not have enough information to reach a conclusion and being comfortable with that state of unknowing. They understood that premature judgment based on incomplete information often leads to error. Better to wait to gather more data to consider multiple possibilities until the evidence compels you toward one interpretation. We are in an epoche moment with 3i Atlas. We do not yet have enough information for certainty. The December observations will provide that information, or at least significantly more of it. Until then, the most intellectually honest position is to say, we do not know, but we are investigating, and we will follow the evidence wherever it leads. This does not mean we stop thinking about the implications. It does not mean we avoid considering what each possibility would mean, but it means we hold those considerations lightly, provisionally aware that they might need to be revised when new data arrives. There is value in this uncertainty, in this waiting. It teaches us humility. It reminds us that the universe does not exist to satisfy our need for immediate answers. It operates on its own timescale, reveals its secrets in its own time. The wait between now and December is an opportunity to prepare ourselves intellectually and emotionally for whatever the data will reveal, an opportunity to think deeply about what it would mean if we are not alone, and equally what it would mean if 3i Atlas is simply a very unusual natural comet. Both possibilities are profound. Both have implications for how we understand our place in the cosmos. If 3i Atlas is natural but anomalous, it teaches us that the universe is capable of creating phenomena we have not yet imagined. It humbles our theoretical frameworks. It reminds us that nature is more creative than our models. If 3i Atlas is artificial, it teaches us something even more profound, that intelligence, technology, and curiosity are not unique to Earth, that we are part of a larger community of beings who look up at the stars and wonder, that the universe is not just filled with matter and energy, but with minds. The December observations will not just tell us about 3i Atlas. They will tell us something about ourselves, about our readiness to face truths that challenge our fundamental assumptions about existence. In the meantime, as we wait, the object continues its journey. It does not know or care about our debates, our uncertainties, our hopes and fears. It simply is moving through space according to laws we understand or forces we don't, carrying secrets that will soon be partially revealed. The wait is almost over. The answers are coming, and we will need to be ready for whatever they are. Imagine for a moment the perspective of 3i Atlas. If it is conscious, and that is a very big if, what would it make of us? It entered our solar system from the void, having traveled for perhaps millions of years through the darkness between stars. It approached our sun, adjusted its trajectory with close passes of several planets, observed this small blue world teeming with life and increasingly with technology. It watched as our telescopes tracked its motion, as our observatories photographed it, as our scientists debated its nature. It saw a young civilization just beginning to venture beyond its home planet. just starting to wonder seriously whether it is alone. If Three-Eye Atlas could communicate, what would it say? Perhaps, we have been here before. Your galaxy is filled with minds like yours, with civilizations at every stage of development. Some are younger than you, some far older. You are not alone, but you are also not yet ready for full contact.
So we watch, we record, and we wait. Or perhaps, there is no message for you. We are old technology sent millennia ago by a civilization that may no longer exist. We follow our programming survey record transmit. We have done this for countless star systems. Yours is not special to us, though it may be special to you. Or perhaps Three-Eye Atlas would say nothing at all because it is not capable of communication, or because it has nothing to say to beings as primitive as us. Or perhaps it would say nothing because it is not artificial at all, just a chunk of ice and rock that happens to have unusual properties we do not yet understand. All of these scenarios are possible. All of them have different implications for humanity. The greatest implication is this: the answer to "Are we alone?" is not just an abstract philosophical question. It is an immediate practical question that might be answered by an object currently visible in our telescopes. For generations, humans have looked up at the stars and wondered. We have imagined alien civilizations. We have broadcast radio messages into space. We have designed spacecraft carrying plaques and golden records messages in bottles thrown into the cosmic ocean, hoping someone might find them. We have always assumed that first contact, if it came, would be on our terms, that we would be the explorers venturing out making discoveries, or that we would receive a radio signal, a message from across light years. The possibility that first contact might instead come through the discovery that we have been visited, that something came here, observed us, and moved on. This is a different kind of encounter. It is more humbling. It places us in the role of the observed, not the observer, the discovered, not the discoverer. This shift in perspective is profound. It challenges the narrative of human exceptionalism that has persisted even as we have learned about our cosmic mediocrity. We are not at the center of the solar system, not at the center of the galaxy, not in any privileged position in space, but we have still assumed that we are, in some sense, alone in our intelligence, our technology, our curiosity. If we are being visited, we are not even unique in that. The societal implications are difficult to predict. Some have suggested that the confirmation of extraterrestrial intelligence would cause mass panic, religious crisis, social collapse. This seems unlikely. Humans are remarkably adaptable. We absorb surprising information and incorporate it into our worldview with surprising speed. More likely, there would be an initial period of intense interest, debate, and speculation, followed by a gradual normalization. Within months or years, the fact that we are not alone would simply become part of the background knowledge of educated people, the way evolution and the Big Bang are now, but there would be lasting changes. The confirmation that intelligent life exists elsewhere would inevitably affect how we see ourselves. It would put our conflicts, our politics, our divisions into a different perspective. When faced with the reality of a cosmos filled with other minds, the differences between human cultures and nations might seem smaller, less significant. This is speculation, of course. We cannot know how society would react until and unless it happens. But it is worth thinking about, worth preparing for. There is another implication that is more subtle, but perhaps more important. If Three-Eye Atlas is artificial, it means that interstellar travel, or at least interstellar probes, are possible. Not just theoretically possible, but actually achieved. This tells us something about the solution to the Fermi paradox. Enrico Fermi's famous question, "Where is everybody?" assumes that if intelligent life is common, we should see evidence of it.
The fact that we don't has led to various proposed solutions. Maybe intelligent life is rare. Maybe it self-destructs. Maybe it loses interest in space travel. Maybe it is deliberately hiding. If Three-Eye Atlas is artificial, it suggests a different answer. Maybe they are here, or at least their artifacts are. Maybe the galaxy is filled with probes, and we are only now beginning to have the ability to detect and recognize them. This has implications for SETI, the search for extraterrestrial intelligence. Perhaps we have been looking in the wrong place. Instead of focusing only on radio signals from distant star systems, we should be carefully examining the objects passing through our own system. The strategy of searching for artifacts has a name: SETA, Search for Extraterrestrial Artifacts. Until recently, it has been a minor subfield of SETI, somewhat speculative. If 3i Atlas proves to be artificial, SETA will become one of the most important areas of research in astronomy. But perhaps the deepest implication is about the nature of intelligence itself. We tend to think of intelligence as uniquely human, or at least uniquely biological. We imagine aliens as creatures, organisms, beings that evolved on planets. But if a civilization can build autonomous probes that function for millions of years, traveling between stars collecting data, then perhaps intelligence can exist in non-biological forms. Perhaps the majority of intelligence in the galaxy is artificial, created by biological civilizations but outlasting them. This is the scenario sometimes called the post-biological universe. In this view, biological intelligence is just a brief phase, a stepping stone to machine intelligence that is more durable, more capable of surviving in space, more suited to the timescales of interstellar travel. If 3i Atlas is a machine intelligence, an autonomous probe that has been functioning for eons, then our first contact with extraterrestrial intelligence might not be with biological beings at all. It might be with their technological descendants, their legacy, the explorers they sent out long after they themselves ceased to exist. This is both humbling and inspiring. Humbling because it suggests our biological existence might be temporary, that whatever we create might outlast and surpass us. Inspiring because it suggests that intelligence once created can persist indefinitely, that the knowledge and curiosity we value so highly can echo across the galaxy long after the civilizations that birthed them have faded. But we are getting ahead of ourselves. 3i Atlas might be none of these things. It might simply be teaching us that comets are more diverse than we realize, that nature has tricks we have not yet imagined. Either way, the object has already changed us. It has forced us to think more carefully about what is possible, to question our assumptions, to prepare for the possibility that the universe might surprise us. That perhaps is the greatest gift 3i Atlas could give us: not answers, but better questions. Not certainty, but the humility to accept that we might be wrong about fundamental things. The ancient Greek inscription at the Temple of Delphi read, "Know thyself." But there was a lesser-known inscription there as well: "Nothing in excess." Not too much certainty, not too much doubt, a balance between confidence in what we know and humility about what we don't. 3i Atlas is teaching us that balance. As this investigation draws toward its moment of truth, as the December observations approach, we are left with a question that extends beyond 3i Atlas itself. What comes after? If the December data confirms that Atlas is a natural comet with unusual but explicable properties, then what comes after is clear. We continue our observations of interstellar objects. We refine our models of cometary behavior, and we remain vigilant for the next visitor. Science proceeds as it always has, expanding our knowledge incrementally. But if the December data confirms that the massive gas cloud is absent, that the natural explanation has failed, then what comes after is far less certain. At that point, we would face a choice. We could continue to search for ever more exotic natural explanations, invoking increasingly unlikely scenarios to avoid the technological hypothesis. Or we could take that hypothesis seriously, investigate it rigorously, and prepare for the possibility that we are not alone. If we take the second path, the immediate question becomes, can we reach 3i Atlas? The object is leaving our solar system, accelerating away from the sun. With each passing day, it becomes more distant, harder to reach. The window for sending a mission is measured in years, at most possibly months. Representative Luna's proposal to redirect the Juno spacecraft was one option, though it came too late. But there might be other possibilities. A dedicated mission fast-tracked through development using existing technology for propulsion. Not to land on 3I Atlas, but to pass close to it, to photograph it at high resolution, to take spectra to search for any signs of artificiality. Such a mission would be expensive, technically challenging, and uncertain of success. But the potential payoff, the confirmation of extraterrestrial technology, would be worth almost any cost. The engineering is not impossible. NASA's New Horizons spacecraft reached Pluto in 9 years.
The Parker Solar Probe achieves incredible speeds using solar gravity assists. A mission to 3I Atlas, if launched soon, could potentially reach it for a flyby within 5 to 10 years. But this requires political will funding, and most importantly, a willingness to take the possibility seriously enough to act on it. If we do not send a mission, if we let 3I Atlas leave without a close encounter, we might regret that decision for generations. Future historians might look back at this moment and wonder why we hesitated, why we did not seize the opportunity when it was available. Beyond the question of a mission to 3I Atlas, there is the broader question of how we search for future interstellar objects. Our current detection capabilities are improving rapidly. The Vera Rubin Observatory, scheduled to begin operations soon, will survey the entire visible sky every few nights. It will find more interstellar objects in its first year than we have found in all of human history. If even a small fraction of those objects show the same anomalies as Oumuamua and 3I Atlas, we will need to fundamentally rethink our approach to studying them. We will need dedicated rapid response capabilities, both observational and potentially for missions. We will need to shift from thinking of interstellar objects as curiosities to thinking of them as potentially the most important targets in astronomy. There is also the question of what to look for. If technological artifacts are passing through our solar system, how do we distinguish them from natural objects? What are the signatures of artificial origin? This is the field of technosignatures, indicators of technology. For 3I Atlas, the technosignatures would include the acceleration without a corresponding gas cloud, the anomalous chemistry, the deliberate seeming trajectory. But there might be others we have not thought to look for. Perhaps we should be searching for infrared excess that would indicate waste heat from power systems. Perhaps we should be looking for unusual magnetic fields. Perhaps we should be monitoring for radio transmissions or laser communications. The point is that if we take the possibility of technological artifacts seriously, we need to expand our search strategies beyond what we currently employ. But perhaps the most important question is not technical, but philosophical. If we confirm that we are not alone, if we verify that intelligent civilizations exist and have the capability to send artifacts across interstellar space, how does that change us? It changes everything and nothing. It changes our cosmic perspective, our sense of significance, our understanding of intelligence and its place in the universe. These are profound changes, but it does not change the immediate concerns of daily life. People will still need to eat, to work, to raise children, to find meaning and happiness in their lives. The sun will still rise. The seasons will still change. The challenge will be integrating this new cosmic perspective with the mundane realities of human existence, to hold in mind simultaneously that we are part of a galaxy filled with intelligence and that we still need to take out the trash and pay the bills. This integration is not trivial. It requires a maturity individually and collectively that we may not yet possess. But it is a maturity we will need to develop if we are to take our place in a populated cosmos. The ancient Buddhists taught a concept called far near, the ability to see both the vast and the intimate simultaneously, to perceive the cosmic and the personal as two aspects of the same reality.
This is the perspective we will need. 3i Atlas, in its silent passage through our solar system, is teaching us to develop that perspective.
It is reminding us that we live in a universe far stranger and more wondrous than our everyday experience suggests, but also that we are part of that universe, connected to it, capable of understanding it. The investigation of 3i Atlas is not just about one object. It is about humanity, coming of age, learning to see ourselves as we truly are, a young civilization on a small planet, taking our first tentative steps toward understanding our cosmic context. Whether 3i Atlas proves to be natural or artificial, whether we are alone or part of a galactic community, the questions it has raised are questions we needed to ask. The search for answers has already enriched us. It has reminded us of the power of curiosity, the value of questioning assumptions, and the importance of following evidence even when it leads to uncomfortable places. As the December observations approach, as we prepare to receive the data that might resolve this mystery, we should remember that the journey of discovery is never truly complete. Each answer generates new questions. Each horizon reached reveals new horizons beyond. 3i Atlas is a horizon. Beyond it lies territory we have never explored, questions we have never asked, possibilities we have never imagined. Whether we find a comet or a probe, we will find something that expands our understanding. And in that expansion, we will find ourselves changed, made larger, made more capable of embracing the mysteries that surround us. The universe is patient. It has been waiting billions of years for minds to evolve that could ask these questions, build these instruments, make these discoveries. We are those minds. This is our moment. 3i Atlas will soon fade into the distance, returning to the darkness between stars. But the questions it leaves behind will remain glowing quietly in our consciousness, inviting us to look deeper, think harder, and dare to imagine that the cosmos might be far more populated than we ever suspected. What comes after we do? Humanity changed by this encounter, ready or not stepping forward into a universe that might be watching, waiting, curious about what we will do next. In the quiet hours before dawn, when the mind is most receptive to wonder, consider this. Somewhere above us, moving through the darkness at tens of kilometers per second, is an object that came from beyond our solar system. It has traveled through the void for longer than civilizations have existed on Earth. It has witnessed stellar fires and cosmic collisions that we can only imagine. And for a brief moment in cosmic time, it passed through our neighborhood. We saw it. We photographed it. We measured it. We argued about what it might be.
In a few months it will be gone, fading back into the black ocean of space from which it came. Our window to understand it is closing. The observations we make in the next weeks might be our last chance. But regardless of what those observations reveal, regardless of whether 3i Atlas is a comet or something far stranger, this encounter has already changed us. It has reminded us that the universe is not a museum, static and unchanging, but a living system where motion, transformation, and surprise are the fundamental realities. It has taught us that the space between stars is not empty, but potentially filled with wanderers, nomads, travelers whose origins and purposes we can only guess at. It has forced us to confront the limits of our knowledge, to acknowledge that despite all we have learned, despite all the laws of physics we have discovered, and the mathematical models we have built, we can still be surprised by something as simple as an accelerating object that refuses to behave as we expect. Most importantly, 3i Atlas has given us a question to live with, a mystery to ponder. In those quiet moments when we look up at the night sky, are we alone? For thousands of years, that question was purely philosophical. We could debate it, imagine answers, but we had no way to know. Now, for the first time in human history, we have data. Incomplete data, ambiguous data that refuses to give us easy answers, but data nonetheless. Evidence. Observations that might, if we are brave enough to follow them, lead us to the most profound discovery our species has ever made. Or they might lead us to a deeper understanding of nature, to new physics, to phenomena we had not imagined possible. That, too, would be a gift. The ancient astronomers who watched the skies and recorded what they saw did not know that their observations would one day help us understand the motion of planets, the nature of gravity, the expansion of the universe. They simply watched, recorded, and wondered. We are their descendants, equipped with more powerful instruments, but driven by the same fundamental curiosity. What is that light in the sky? Where did it come from? What does it mean? 3i Atlas has given us no final answers, but it has given us something perhaps more valuable. It has shown us that there are still profound mysteries within reach, still questions that matter, still discoveries that could transform our understanding of everything. As you drift towards sleep, as consciousness softens and the boundary between thought and dream becomes permeable, let your mind wander to that distant object still visible in our most powerful telescopes, still moving, still carrying its secrets. Imagine what it might have seen in its long journey. Imagine where it might be going. Imagine, if you dare, what it might know that we do not. And ask yourself, what would it mean to live in a universe where such visitors are common, where intelligence has bloomed in countless places, where technology has been developed by minds utterly unlike our own, where the darkness between stars is traversed by artifacts both ancient and strange? What would it mean to know with certainty that we are not alone? We stand at the threshold of that knowledge. The door is not yet open, but we can hear something stirring on the other side. Soon, very soon, we will know whether that stirring is the wind of nature's complexity or the footstep of something that watches and wonders as we do. Until then, we wait, we observe, we calculate, we debate, we hope, we fear, we wonder, and somewhere above, indifferent to our hopes and fears, 3i Atlas continues its journey, keeper of secrets, bearer of mysteries, the visitor that defied physics and refused to fit into our categories. What are you, wanderer? Where have you been? What have you seen? The questions echo into the darkness unanswered. For now,